Okay, so because the time is short, let me launch right into do's and don'ts of deep learning for development. All right, so it says 5, I cut down to 3. 3 key choices you must make as a deep learning researcher. What problem will you address? Number 2, what machine learning method will you use? Number 3, what best practices in applying the method? So I think all 3 of these are very important. I will focus primarily on 2 and 3. I may say some things that are fairly controversial. I will try to leave some time at the end for discussion. I started at 3:36, so I will try to finish at, well, that's my time, 3:36 a.m. I'll try to finish at 4:06 a.m. so we have some time for questions. All right, so this part, what problem will you work on? I'll pass over this quickly. If we have more time, this is something we can discuss. But I think this really, in some sense, is the most difficult part of the research. What are you actually going to work on? And I would say it's the area that I personally have been least successful. But I think these 3 principles are good ones, and I'll illustrate how they work. Number 1, let the problem find you instead of you looking for the problem. Number 2, position yourself to be found by the problem. Number 3, be swift to hear, slow to speak. Now, it's interesting to me that from the Bible, which gives eternal wisdom, we find a good example of this. I'm not going to go into this example in detail. Just to remind you, if you know the story of Joseph, I think the story of Joseph is familiar both to Christians and to Muslims, which I think is most of you. If you remember, he had dreams. When he was young, he had a dream. And what it brought him was trouble. He was thrown down a well and became a slave. Later on, he interpreted a dream, and it brought him honor and made him ruler of Egypt. What was the difference between these 2 dreams? The first dream was his own dream. The second dream was somebody else's dream. So the takeaway is, if you want your research to have an impact, interpret somebody else's dream. I'll leave you with that. If you want more detail, you can ask for my presentation. Let me give a practical example of this. Stephen Strogatz, a Bachelor's of Science student. So as a math major, he was interested in the structure of DNA. So he studied some mathematics that was related to DNA. He also studied biology. Because he wanted to do research that had impact, he talked with biologists and proposed several research projects to them based on his understanding from a mathematical point of view. They told him that what he was saying was nonsense, that things don't really work that way, and that what he was talking about was theoretical and unrealistic. But he continued to go to biologists and listen to what they had to say, and then the professor of biology told him about an important problem that none of them could solve. So one thing to recognize is that Stephen had to understand enough biology to understand what the problem was. And that takes time and effort. So once Stephen understood the problem, he said, well, that's easy. I can solve it immediately. This was a problem that had been puzzling them for weeks. But because of his different background, he was able to have insight into solving this problem. Later on, even as a Bachelor of Science student, he published in one of the most prestigious journals in the United States and has been cited 270 times. And in fact, Stephen Strogatz is now professor of mathematics at Cornell University. And I happen to know him because he was my classmate. So that was a very influential example to me. Okay. So I think, so if you want your research to have impact, the choice of problem is critical. And so I'm going to pass over this quickly. I think there are 2 approaches to this to have a research that has impact. One is to try to apply deep learning directly to problems of interest to development. One of the issues is that much deep learning research in developed countries is addressing problems that is of no interest whatsoever to developing countries. If you're in a country where you don't have reliable electricity, you also have poor internet and deficient infrastructure, why are you worried about game-playing algorithms or self-driving cars? In fact, these are things that you don't want, because self-driving cars would put thousands of taxi cab drivers out of business. And that's not something that's going to be very helpful to society. All right. So one takeaway for me is that researchers in developing countries must develop their own priorities and not simply follow along with developed country research. Now, the other way to use deep learning to help development is to serve the developed country community. Now, I give this example. Nigeria's total exports are $34 billion, and that's about $170 US per person. If you go to India, information technology, that's computer support, programming, etc., information technology is $147 billion in exports every year. So that's more than 4 times the Nigeria's total exports, which includes oil, raw materials, everything. Everything that Nigeria exports is only $34 billion. Now, you could say that India is a much bigger country, but this comes out to $107 per person for information technology alone, which is 2/3 of Nigeria's total exports. So I would propose to you that Nigeria does not have a poverty problem. Nigeria has a productivity problem. So increasing your productivity, increasing your exports, and exports can include IT knowledge. IT knowledge includes the ability to use machine learning to solve problems in the rest of the world. All right, so those are 2 different approaches I see to applying machine learning to development. One is trying to attack development challenges directly. The other is to increase income by developing expertise in areas that the developed world needs. All right. So let's pass on to my second question. What machine learning method do you use? And I do like to illustrate. A picture is worth 1,000 words. On the left here, this is a hydraulic hammer, a very high-tech tool that is extremely powerful. This you see housed in red. Here's a pile that this hydraulic hammer is driving into the ground. Extremely powerful tool and very well developed. Okay. Now, here is my friend who wants to hammer a nail into the wall and hang a picture. Now, I have this very powerful hammer. I say, look, I can solve your problem. I have this wonderful hammer, high-tech hammer, that can hammer anything. Now, if you use this high-tech hammer to hammer a nail into the wall, you will both destroy the wall and the picture, and you will not accomplish your goal. You don't choose the hammer based on, don't choose the nail based on the hammer, you choose the hammer based on the nail. This is not an appropriate tool. Similarly, you should choose the machine learning method based on the data. Start with the data. Unfortunately, I see all too many times researchers, particularly graduate students, who say, I want to use machine learning. I want to use deep learning. I want to use recurrent neural networks. And they have some problem for which recurrent neural networks is completely inappropriate. You start with the problem, which means start with the data, and then decide what method you want to use based on the problem. A problem-centric approach rather than method-centered approach. You choose the method to solve the problem. All right. So when can you use deep learning? There are many, many researchers who are using deep learning for inappropriate topics. Deep learning requires lots of data. Lots of data. And you will find many papers who are trying to apply deep learning to a few hundred data points. And I would submit to you that a lot of this research is, to put it bluntly, garbage. And I will give you some examples later on. Now, I hope that you will not generate garbage. There's enough garbage in the world already. You need lots of data to develop deep learning. An example is, deep learning is an example of learning, just like young children learn. Young children learn by many, many, many examples. You want the child to learn arithmetic. You give them many, many, many examples, many problems. That's how they learn. Deep learning is like this. Now, there is some possibility of transfer learning or data augmentation. These are techniques where you use machines that are trained on very large data sets and then bring them over to situations where you don't have so much data. So that is a possibility, but I think it's also a very dangerous one because you are making inferences that may or may not be justified. So, but those are two techniques that are quite powerful, and are areas of active research. Now, deep learning should be used with complex, subtle features that are difficult to characterize, especially image data. Now, images can be photographs, or they can come from medical. You can get from medical scans or geospatial data. That's another way to get image data. But you need lots of images. For instance, 1,000 images. Lots of images to train your deep learning. And the deeper your neural net, the more images you need. Deep learning can sometimes be used with time series, like weather data or serial sensor data. Sometimes. I think many times it should not be. And again, I'll give some examples later on. Deep learning can also be used for human-generated texts, speech, and music. So this has been a demonstrated application. For instance, people monitor social networks for opinion mining. You can see that many businesses are very interested in deep learning because they want to know customer sentiment. And this is a very great potential area for revenue generation because this is a real fad in most developed countries and in companies. All right. When not to use deep learning. Deep learning should not be used for smaller to middle-sized data sets or data with few features or few alternatives. For example, if you want to use deep learning to analyze, if you have a 16-question yes-no survey that you administer to thousands of people, you don't want to use deep learning for this because mathematically you cannot improve on decision tree. Right? The features are not complicated. 16-question yes-no survey, that means you have 2 to the 16th possible outputs. You can characterize the probability distribution completely. You can't improve on decision tree. Deep learning is just a lot of fancy machinery for no good reason. If you want to use deep learning, it should be something that's fitted. You need to understand what deep learning is doing and what approach it's taking to the data. And I will talk about that shortly. Okay. Now, if you don't use deep learning, what can you use? You can use statistics. Okay, this is another area that I do emphasize quite a bit. I find many people in machine learning have very deficient knowledge of statistics. And I will tell you that probably if you don't know statistics well, you are probably misusing deep learning. If you don't know statistics well, you are probably misusing deep learning. Learn the classical techniques first. Learn the easy techniques first, like hypothesis testing, regression, logistic regression, partial regression. There are many classical techniques that can often be applied to analyze your data very well. Now, if statistics doesn't work, you can move on to classical machine learning. There are some other algorithms that are much easier than deep learning and also perform very well and are very powerful, like K-nearest neighbors, decision tree, rainforest, support vector machines, extreme gradient boosting, Bayesian. There are lots of methods like this. Don't jump to the fancy method. Simpler is better. All right. So in order to decide what machine learning method you do use, you should understand your data thoroughly. You should take time to understand what your data is, what the nature of your data is, the deficiencies of your data, what the data is telling you. You should try to visually represent your data, understand how different parts are related, understand the mechanism that makes the data behave the way it does. You should also understand how deep learning uses data. What is deep learning doing with the data in order to draw its conclusions? And I will say that correlation is the key to method and feature selection. When you use deep learning, you have to select both the architecture of your neural network, and you also have to select features. You have, for instance, if you're using a convolutional neural network, you need to know how many layers, how many nodes per layer, what kind of kernel size, etc. These are system decisions. You also need to decide what features you're going to input into your neural net. That's feature engineering. Both of these are important, and you need to understand how correlation is how deep learning is relying on correlation. Correlation is a statistical term, and it has a statistical definition. But you can understand correlation as saying two things that have a relation. If I know something about one thing, then that will give me information about another thing. So let me give this example. Again, I like to give visual examples. How do you look for a needle in a haystack? This is a common proverb, looking for a needle in a haystack. So here's your needle, and here's the hay. Very, very difficult to find if you try to sort through the haystack and look for the needle. So what do? Well, one thing that will help is you get a magnet, because the needle is attracted by the magnet. Okay, so what does this mean? The magnet is homing in on a distinctive feature of the needle. Okay, machine learning can do exhaustive search through your data, but you have to, if you want your search to be effective, you need to identify features of what you're trying to find. You need to identify these features and direct your machine to look for these features. I would say an even better way to find a needle is to use a metal detector. Right? So the metal detector is looking in areas for a specific feature of the needle. It's not just sorting through one by one and seeing, well, is this a needle, is this a needle? It's looking for distinctive features. The same principle holds in machine learning. Okay, let's see. All right, so here's an example in image data. How do you look for features in an image? Now here's a picture of a fully connected neural network. I'm not going to go into, I assume that people know something about this kind of diagram. If you know anything about deep learning, you've seen diagrams like this before. But these are nodes, these are nodes arranged in layers, and they're connections. So this node will influence all the nodes in the next layer, and so on. Everything is connected. Now, to configure this network, you need to assign a number to each one of these edges. Okay. So, in fact, what you're doing with this network is you're looking everywhere for everything. This is like looking for a needle in a haystack. You're saying, well, it could be anywhere, so I'm going to look everywhere, and I'm going to look at everything. That's not efficient. If you know something about your input data, for instance, if you know you have an image, images have local features. For instance, this picture of a robot has an eye. That's a local feature. That only involves pixels in a small area. So I'm not looking for an eye all over the picture. I'm looking for pixels that are close to each other. So that's what a convolutional neural network does. It looks at small pieces of the image at a time. And it doesn't look at the whole image at the same time. It looks at small pieces of the image separately. And then based on these small pieces, it tries to find things that could be useful, and then builds these up step by step. Here you could have 4 features, then you go to 8 features, and so on, and then you match this against several options, and then you produce your output. Is this a robot or not? And you can recognize your image. Okay. So again, looking for specific features, not looking in general everywhere. All right. So one example to show how to understand how deep learning uses data, I'm going to put my chat on. Can anyone tell me what this is a picture of? You can type into the chat window. Can anybody recognize this picture? Very good. Okay. All right. You see the power of the human mind. This has a few squiggles here and there, and only suggestions, this is in fact an elephant. Now what did your mind do? Your mind identified several features that are characteristic of an elephant. The tusk, the ear, the eye, the toenail, the trunk. And it put everything together and said, this is an elephant. This is exactly what machine learning does. It looks at pieces, identifies characteristic features, and then based on these features, here you identified maybe 5 or 6 features that are characteristic of an elephant. And you say, these features match an elephant. I think this is an elephant. This is exactly what deep learning does. All right? So, all right, here's your elephant. You can see that. Okay. So what deep learning has done is it has correlated the input with distinctive features. So here I have this. Let me see if I put this on my screen clipping. So you start with a bank of filters, and these filters, these initial filters are very small. They're looking at very, very small sections of the image. Now, how big should you make these? How big should you make these small filters? Well, that's a design decision that you should know if you understand your data. You don't just make that choice arbitrarily. You need to understand what size features you're looking for. So these small features are looking at primitive local features. They may look for a vertical segment or diagonal segment. I have a picture that shows this on the next slide so you can understand more clearly. All right, so each one of these small features will assign a number to each one of these possibilities. So let me just put my number between 0 and 1. Maybe this number is 0.1. This number is 0.3. This number is 0.7. This number is 0.03. Now what these numbers are representing is the confidence that this feature has been identified. Now this filter bank may apply to a neighboring patch of the picture, and this will give some other set of numbers, 0.2, 0.7, 0.6, 0.1, and so on. So you get numbers for all of these filter banks. Then these primitive features feed into composite features. Okay? So what the primitive feature does, this composite feature looks at these numbers here and looks at the pattern of numbers and says, well, based on these numbers, I can assign a number to each one of these. Larger number means I have a higher confidence that this feature is actually being represented by the image. So maybe this one turns out 0.9, this one turns out 0.1, and so on. Okay, so here I get numbers here. Then I do the same thing again. I put these together here. And you put these composite, there may be several layers of these composite features that become more and more complex. The point is to recognize distinctive structures. You remember in the elephant, you saw a round ear. That's because your mind put together this, your mind put together this, go back. Your mind saw this curve and said, well, this looks like this looks like an elephant-shaped ear. So what the machine does would be break this image up into small pieces. Here it sees a diagonal segment. Here it sees a small curve, another curve. Here's a straight segment. And put these together and says, well, this looks like a round ear. Okay, so it identifies this feature with a high confidence. Maybe it has a fairly high confidence here. It may be 0.7. All right, it looks for a pointed ear and says, well, it doesn't look like a pointed ear. Maybe the confidence here is 0.2. For eye is very high confidence for this, 0.9. I see something that looks like legs, maybe 0.6. Straight tail looks like it has a straight tail. Let's say I see something looks like a straight tail. I'll say 0.5. I don't see anything looks like a fishtail. That's maybe 0.01. I see some toenails, 0.3. I don't see any claws. That's 0.1, and so on. What you do is you take this vector of numbers and you correlate it with the elephant vector. Now we know that elephants have round ear, pointed, and they don't have a pointed ear. They have eye. They have a leg. So we know round ear has a 1. Pointed ear has 0, eye has 1, legs have 1, straight tail has 1, fishtail has 0. So here we have this vector that represents an elephant. So what you do is you take this vector that represents the features that the deep learning network has gleaned from the image, and you match this together. Mathematically, what you do is called a correlation. You multiply these two numbers together and then you add. If this number is large, then you have high confidence that what you see is an elephant. If the number is small, you think you say that this is not an elephant. Okay, so in the case where you identified an elephant, you found several features that matched features of an elephant. So that's how you identified an elephant. So that's how convolutional neural networks work, and that's how neural networks work in general. So let me go back to my picture here. Okay. All right. So you have this hierarchy of features. Okay. I really am going over my time. So let me go on. Let me move on. Okay. So I do want to get to other data. So you should say, what type of features are you looking for? If you're looking for an elephant, you should think about what type of the characteristics of every feature. Are they local? Are you looking for local structures? Are you looking for extended regions of the same color? Are you looking for repeated patterns? Are you looking for enclosed area? What type of features are you looking for? You need to help the deep neural network look for these features. Artificial intelligence is an enhancement and not a replacement for human intelligence. An example, a tennis racket. You cannot play tennis without a tennis racket, but the tennis racket is still guided by the player. The player has to move the tennis racket to the place where it can meet the ball. Okay? This is what AI does. AI does not replace human intelligence. You need to show your AI where you should be looking. So one application would be license plate detection. Okay. Now you know something about the license plate, what you're looking for. License plates have straight edges. Within the straight edges you have characters, and those characters have certain specific shapes. Right? So you have stages that you should apply to your image. You're looking for shapes, so you convert to grayscale. The color is not going to help you. You want to detect curves. You want to convert to binary. I'm not going to go into the details here. But all of this first part is pre-processing before you get to deep learning. You develop your data to the point where deep learning can look at it intelligently. And you develop such a kind of flow diagram. Okay. All right. Now, I talked about image data. You can also have temporal data, data that varies in time. You need to look at the features of your data that varies in time. Is it periodic? Are there persistent memories? Is there temporary forgetting? Are there pulses in the data? You need to take this information and use this to design your features. Another classic example is looking for a lost key. This man is looking for his lost key. He's looking here because there's light, but the key is not here. The key is over in the dark. He's looking in the light because it's easy to look here. All too often, people in research, they look for something in a place where it's easy to look, and that's not where the thing is. You need to show the machine where to look. It may not be an easy place to find it, but you need to direct the machine to look where the object is going to be. All right. So, for instance, this was some data that was actually brought to me by a student. He wanted to use deep learning to analyze sensor data. This is sensor in a room, and this was data taken by University of Berkeley in US. And I think it's on Kaggle, a source of data where a lot of people get data. And he wanted to use deep learning to analyze this. Now I asked him, what do you know about the data? Have you plotted the data? He said, no, I don't know anything about the data. He had taken the data and he used some fancy method like LSTM with a window size of 3,500, and he had done something with it. And I said, have you even looked at the data? He said, no. And I said, well, look at the data and see what's going on. So he plotted the data and he said, what do you notice about this data? Okay. Now you can see, as a human, you can see certain patterns. This is called periodicity, right? You get or seasonality. You have a regular pattern of data here. Now notice something here. Here, if you look at the intervals here, these intervals are extremely regular. Okay? They're always exactly the same. Now once you get to this green, the interval length goes off. This interval length is not the same as this interval length. You need to ask yourself, why is the data behaving regularly like this? And the answer is, this is data in a room. The room's characteristics are different in the day and in the night. When people are present in the office, you have a certain temperature profile. Yes, okay. All right. So when people come into the office, the temperature rises and then the temperature goes down during the day. Right. So there's a reason for this pattern. Now, when the student applied his deep learning, he lost the pattern because he was not looking for periodicity. His prediction lost the periodicity because he did not take that into account. You need to use an approach that takes the periodicity into account. There's something in statistics called deseasonalization. Use these statistical techniques before you apply deep learning. Another thing that I noticed here was that the red curve was data that he had, the green curve was data that he predicted. In fact, if you think about it, this prediction is just ridiculous. You cannot predict. How can you predict something like this is going to happen in a room 2 hours after you enter the room? And you see this kind of thing also in weather prediction. People make ridiculous predictions. You cannot predict a thunderstorm in 2 weeks. It's just not possible. You need to orient your method to predict things that are possible. You do need to use common sense. Okay. So there are various techniques within deep learning to accommodate periodic data. If you do have periodic data, you can use Fourier transform, which looks for characteristic frequencies. You can include an index that tells seasonality. If your data has other features, there are other techniques for extracting these features. Okay. Simpler is better. Here's one example. I have to go quickly because my time is nearly gone. When people wanted to analyze texts generated by human to discover meanings, they started out using deep networks because deep networks were so successful in image processing. So they had several layers to convert words into vectors. We've seen already how deep learning converts information into vectors. So the first systems that did this used deep learning. Later on they found this is way too complicated. We don't need so many layers. We use one layer. We don't use what's called an activation function. We use a simple linear neuron. In fact, this is not a neural network anymore. It's just simply a matrix. So they went from complicated to simple. It probably would have been better to go from simple to complicated. Always look for the simpler solution and not the more complicated solution. All right, let me go to techniques. Okay, let me go to techniques. There are some techniques that you do need to use on your data. Quarantine your test data. If you know about deep learning, you have to train your neural network and then you have to test it. These are two completely different functions. If you don't quarantine your test data, then your test is useless. We have the example of COVID. If someone has COVID, if you quarantine too late, it's too late. If you start your quarantine after a person in your population gets COVID, it's too late. Nigeria closed the borders to prevent COVID from coming in. But if there are people inside Nigeria who already have COVID, it's too late. All right, so I'll give some examples of this. Okay, you need to establish a simple baseline. Even in cases where you do use a complicated algorithm, you need to compare it to a simple baseline. While you're analyzing your data, you need to ask yourself, does this make sense? Understand the signs of what you're doing. There are various visual representations of the process of deep learning that give you warnings and indications whether your process is working correctly. And if possible, compute error bars. Very often in the deep learning literature, they will say, Well, this method is 98% accurate. This method is 96% accurate. This method is 90% accurate. Whenever you make an accuracy estimate, you never have an exact number. There's always a plus or minus. Whenever you measure a temperature, I can't say that it's 98.55 degrees. It's 98.55 plus or minus some uncertainty. There is an uncertainty in every estimation. Unfortunately, in the deep learning literature, they rarely compute these errors in estimation. So they say this method is 98.7, this method is 98.9, 98.9 is better than 98.7. This is garbage. You don't know that's true unless you know the error bar. It's possible that the difference is simply random error. Right. Quarantine your data. Data leakage produces inflated accuracy values. This, unfortunately, is all too common in the deep learning literature. We did a study, a survey of papers that used used machine learning for weather prediction. 50% had data leakage, meaning that their test results were suspect. Here's an example of data abuse. And this is a published paper. In fact, the same authors published another similar paper and made the same mistake. Here we have some data that they're analyzing using a neural network. All right. So what they did was they took 10 samples and they took 3 measurements on 10 samples. You can see this number, 6.97. So that's the first sample. They took this same number, took same number and measured it again, 6.95, almost the same. 13.94, this time 13.96, 8.54, 8.64. So they took 3 samples, they took 10 samples, 3 measurements on this sample. What they did was they took all of this data and they divided it into training and testing. Some of the data was training, some of the data was testing. Now, some of these samples went into the training, some went into the testing. For instance, this first sample might have gone into training, and then this sample went into testing. Now, of course, your testing data is almost an exact duplicate of your training data. So what you're doing is you're cheating. It's like you're studying for the test, and you have the test questions that you're studying from. So of course you're going to do very well. And in fact, they have almost perfect fit. But this perfect fit, in fact, is garbage. Complete and total garbage. Because you're using what you're trying to predict what you're trying to predict. If you already know the answer, why do you need to guess the answer? So unfortunately, this is what happened. Okay. So we did a study so that's one point. You need to avoid data leakage. Establish a simple baseline. Again, we did a survey of machine learning models for rainfall prediction. Out of 66 papers, all these papers use very fancy methods with machine learning. Because they want to publish, they want to show something new. Almost 50% did not provide a baseline. So you don't know if their method provides any improvement or not. It may be just as effective as the very simple method. And in fact, we did a study, this is also a published paper, where we compared very, very simple baseline to some of these more complicated methods. Multilinear regression, K-nearest neighbor, XGBRF, all these. Now this y-axis here is the error, the mean average error, and the x-axis are different feature sets, and the different colors are different methods. This black line down here is what we obtained when we simply took the average of previous data. Just use average of previous data to predict the next data point. And in fact, this gave us less error than all of these fancy methods. Okay? So don't waste your time. Make sure that you're getting some results that mean something. Okay? All right, understand the signs. This is a curve that was brought to me by a student. He's showing how he was training his model. Again, I can't go into details because my time is up. Here we have the training loss and the test and the validation loss. Again, if you know something about deep learning, during the training process, you do training on most of the data, then you do validation to see how well you're doing. So he had these curves, and he showed me these curves, and I said, did your process work well? He said, well, it looks okay. And I said, there is something deeply wrong here. There is something extremely wrong here. If you look at this validation loss, this does not make sense. What is the validation loss telling you? Validation loss is telling you how well you're doing after each training. This is like studying for an exam. You fail the exam the first time. All right, so you go back and study again, then you do worse. Okay, so this is the initial loss, this is the loss the second time. This enormous increase in loss. So the first time you take the exam, you get 80% correct. Second time you take the exam, you get 50% correct. Now that might happen with a human being, but it does not happen with a machine. If you're doing any kind of training, you're not going to get worse on the second try, and you're not going to get that much worse. Something is wrong here. You need to understand the warning signs. Okay? I find all too often people simply represent their data and they say, well, this is what the data is doing. No, what does the data signify? All right, the same student brought me this, the student that I said before brought me this here and said, well, here is my predicted sequence, which is the green, and then the true value, which is the dotted line. So let's see here. So the question is this red a good prediction of the green? No, it looks fairly close. But in fact, this red is a terrible prediction because again, my time is up, but you need to look at your data and say, does this make sense? If it doesn't make sense, then you need to go back and look at it. Don't just present your data and present what it looks like. Right? Give error bars if possible. Here we have several results. This also gives the prediction error for different machine learning methods. All right, these are different features, and the different colors are different methods. Question: is this green method better than this red method? Okay. The error is less. This error is 95. This error is over 100. So the green method is better than the red method. Is that right? Well, the answer is no. The green method is not better than the red method because we have these error bars. We have this value, but we don't know that the value is this value. It's somewhere between here and here. This red value is somewhere between here and here. There's an overlap. It's quite possible that the red is better than the green because there are error bars. You need to have error bars. Otherwise, you cannot draw any conclusions. Okay, okay. All right, so here's the summary. So what problem we address, let the problem find you. But position yourself to be found. Make yourself available. Listen to other people. Listen to people in the area. What are they saying? What problems are they concerned with? Be swift to hear, slow to speak. What machine learning method will you use? Let the data determine your method. Understand your data thoroughly. What makes the data behave the way it does? What are the interesting features in the data? Correlation is the key to method and feature selection. You make these decisions based on what type of things you want to correlate. Simpler is better. Don't use the fancy method. Or if you do use a fancy method, use a simpler one also. Try to use the simplest method possible. What are your best practices? Quarantine your test data. Establish a simple baseline. Ask yourself, does this make sense? And if possible, compute error bars. Yeah, I think that I am finished. I think if I went over, I apologize, but thank you for your attention.
This doctor also commend you for